Okay, so here's another PE HVAC question. So the question states, a pressure gauge right at the discharge of a water pump reads 75 psig for a flow rate of 85 GPM. The pump efficiency is 75% and the brake horsepower is 2. The suction and discharge pipes are both Schedule 40 4-inch steel pipe and the water temperature is 150 degrees Fahrenheit. Under these conditions, what is the net positive suction head available? Okay, so first let's draw a little diagram here. So we have our inlet, our pump, then our outlet. We know that there is 85 GPM over the pump. The pump is 2 brake horsepower, and it is 0.75 or 75% efficient, so 0.75. And we also know that the discharge of the pump is 75 psig. So 75 psig. And the temperature is 150 degrees Fahrenheit. So we need to find the NPSHA. So if we go in our handbook, we can sort by net positive, and it will give us 2 equations for a net positive suction head available. This one kind of deals with a newer system. So you have the horsepower of your pump, the vertical distance, vapor pressure, and then the friction head from your fittings and equipment. But we don't know all these values, so we're going to use this one because we can find the velocity from the GPM, we can find the vapor pressure from the temperature, and we can find this inlet suction head from the pump horsepower equation. So I'm going to go ahead and grab this guy. So first, let us get this vapor pressure. So if we go to our PE handbook and go to engineering, no, it's properties of materials, and then properties of water atmosphere pressure. So we have properties in Celsius, but we really need that in Fahrenheit. So go to the next page. I guess Fahrenheit here. And we know our water temperature is 150 degrees Fahrenheit. So this guy. And that corresponds to a vapor pressure of 3.72. So we're going to grab that guy. So pressure vapor is 3.72 psi. Now all our values are in head, so we need to convert that. So we multiply that by 2.31. Put that in my calculator. It's 8.7. So 8.7 feet head. So we have this guy. Well, then we can get this atmosphere head pretty easily. So pressure atmosphere is, well, atmosphere at sea level. So 14.7 times 2.31. Calculate that. 33.96 feet head. And then let us find this guy. So HS is going to be the pressure head at this inlet to the pump. And we're going to need the pump horsepower equation. So if we go to our PE handbook and search up pump power, we're going to grab the brake horsepower pump equation. So we know this guy, we know the GPM, and we know the outlet of the pump, which is H2. So we're trying to find this inlet H1, or what we're calling HS here. So HS. So if we plug these in, so 2 brake horsepower equals 85 GPM times H2, which is 75 psi G. So yeah, so we need to convert that 75 psi G to head. So I'm going to multiply this by 2.31. Which gives us 173.25. So this should be 173.25 minus HS times 1, specific gravity, divided by 3960. And then we know our efficiency is 0.75. So times 0.75. Okay, so I'm going to rearrange to solve for HS. Plug that into my calculator. 2 times 3960 times 0.75 times 85 minus 173. Oop, I did something wrong here. Let me redo that. Okay, so HS equals 103.4 feet head. So that's our inlet pressure. Now we need to find our velocity. This is our dynamic head here. So we can find the velocity through the GPM. So we have 85 GPM, or I like to write it out like gallons per minute. And we need to convert that to feet per second. So we have 1 minute, 60 seconds, and then 1 gallon equals 0.134 feet cubed. And we have a cubic foot, so we need to divide by a squared foot, which is our area. And we can get the area from the diameter of our pipe. So we have a 40-inch nominal pipe. We could use this 4 inch as our diameter, but if we go to our PE handbook and search up Schedule 40, so what was our type size? 4 inches. So over 4 inches, our diameter is actually 4.026, so it's slightly larger. For our calculations, it really wouldn't matter. We could use this or the actual inside diameter, but I'm going to use this guy. It also gives us a flow rate in inches squared. So I'm going to grab 12.724. So 12.724, and that was in inches squared. So we need to convert the inches squared to feet squared. So 12 inches squared, or 12 inches squared is equal to 1 foot squared. Okay. So when we cancel all these, we should be left with feet per second. And I'm going to go ahead and plug these numbers into our calculator. So 85 divided by 60 times 0.134 divided by 12.724 times 12 squared. So that gives us 2.15 feet per second. So we can plug that into this v squared here. So v squared over 2g equals 2.15 squared divided by 2, 32.2. I'm going to plug that in my calculator. Squared by 2 divided by 32.2. Okay. So we're left with 0.072 feet head. That seems very low, but we'll go with that. So we should have all our parts here. So we can plug all these guys in to this equation to get our NPSHA. So we have HA 33.96 plus HS. So the vapor head, which is 8.7, plus velocity head, which is 0.07, minus, oh, this guy should be, that's HS, that should be 103. And minus our vapor head, which is this guy. So 8.7. So if I plug that into the calculator, I am left with 128.73. If I go to our selection here, 130 would be the closest answer. So B is our answer.